Hello everybody, today we will discuss that elastic stress components, what we can formulate using the finite element based method. And actually once we look into this finite element formulation, then before that we need to understand that what way we can relate the stress and strain. That is very simple way. If we look into the elastic component or elastic stress analysis part, then how we can integrate, that means what we can find the relationship between the stress and strain in the different form, different matrix form we can find out, and accordingly we can relate between these two components. So, to do that, first we look into the elastic strain component. So, we know that the components of the strain in individual x and y and z direction, and we know that epsilon x, the strain in direction x equal to, there are three components are there. So, if we look into that elastic stress versus elastic strain, and that is related by the Young's modulus, and when there is a acting of the one directional stress or one directional strain. So, in that case we can simply stress equal to, we can write that E into strain. E is the Young's modulus or elastic modulus, and this is the stress and this is the strain, and that is correct in case of assuming that there is a unidirectional load or unidirectional stress is acting. But this stress versus strain, that we can see, that we know the stress is proportional to the strain within the elastic limit, and then if we look into the once elastic stress comes, some part of is the elastic and then it depends the plastic zone. So, plastic zone is the non-uniform relation between the stress and strain. We assume this is the strain axis, this is the stress axis. So, this path is linear. So, when this path is linear, then we can simply relate between the stress and strain Young's modulus, and since it is one dimensional, then we can use this particular relation, the relation between the stress and strain. Now, if even it is elastic stress or elastic strain components associated with the all x, y and z direction, then what the strain in one direction can be related to the with the strain component in other direction in terms of the Poisson's ratio. So, the lateral strain by linear strain. So, that is ratio can be defined as a Poisson's ratio. So, therefore, we can link between the two different direction strain in using the Poisson's ratio value. So, that comes into this picture. So, if we assuming the strain component, but strain component is the normal strain component. So, normal strain epsilon x. So, we can say that epsilon x having the one component is the sigma x by E. So, here that we are getting the stress is here, the strain component is basically sigma by E. So, if x direction strain is acting, so sigma x by E is the one of the strain component, and that strain is induced because of the stress along the x direction is the sigma x. Now, other direction, what may be the strain? So, in other cases the strain lateral contraction may happen in the other direction. So, this Poisson's ratio into sigma y divided by E, and that other sigma z by E is the basically strain component, but when you multiply by the Poisson's ratio, it indicates what is the effective value of the strain along the x axis. So, effective strain along the x axis by considering the effect of the all three different stress components can be written effectively is like that. One sigma x the positive, because along this direction we assume the strain is the positive value, and then Poisson's ratio we introduce, and then we can use the sigma y and sigma z, minus of that divided by E, all indicates the strain because of the sigma y and sigma z, and that is acting along the x direction, that is the along the normal, takes care of the strain components along the x axis. So, this is the effective strain accounting all these three stress components, and then which is modified by this Poisson's ratio, we can get the effective strain along the x axis. Similarly, along y axis, what is the strain value? The sigma y by E minus of the strain components because of sigma x and sigma z, and that is the effective strain along the y axis. So, similarly, epsilon z also we can estimate the effective strain sigma z by E minus of, we can take the that other strain components because of the stress sigma x and sigma y. So, that is why effectively we can write out this three different strain components along x, y and z direction is the epsilon x, epsilon y and epsilon z. Now, E is the Young's modulus and values of E are usually determined from the tension test. So, uniaxial tensile testing, the data if we get, and from there we can find out what is the value of the Young's modulus. It basically simply indicates the slope. So, means we can, if this is the strain value and this is the corresponding stress value, the yielding start at which point, and that from there the data we can estimate what is the value of the Young's modulus and a particular uniaxial tension testing of a particular sample. Now, apart from this normal strain component, there are also shear strain components also there. So, shear strain component is directly related to the shear stress value in terms of the shear modulus. G is the shear modulus, and what value of G usually determined from a torsion test. So, if we look in the pure torsion test, from the torsion test we can estimate what is the value of this value of the G, or shear stress versus shear strain, or T versus the torque applied and T versus theta. From there also we can estimate what is the value of the this shear modulus. Now, shear modulus also within the elastic limit, the shear stress is proportional to the shear strain. So, stress is proportional to the shear strain, and constant of proportionality G is the known as the shear modulus. So, similarly tau xy equal to G gamma xy, tau yz equal to G gamma yz, and tau xz equal to G gamma yz. So, that is why this the relationship between the strain and stress, and if you look into overall, the relation between the stress and strain is established using this three different, the Young's modulus is one constant, and the shear modulus and the Poisson's ratio. These three components we have considered to find the relation between the stress and strain, and strain can be both normal strain components as well as the shear strain component, and stress can be both normal stress as well as the shear stress component. So, once you get this relation between the stress and strain, but only thing is that what we can arrange these material properties, basically Young's modulus, shear modulus and Poisson's ratio, these are the it is a material property. So, different material, the values of all can be different also. So, therefore, that is well defined, or maybe we can well established properties of the particular material, and because this material properties has been already derived from some testing, from experiments actually. Now, once you know this value, we try to relate between the stress and strain in the vector form, or in the by introducing the matrix form, we can relate between the stress and strain. That we will see how we can relate between these two. Before that, two usual condition, that is a plane stress and plane strain conditions is sometimes used to solve in kind of the particular engineering problem also. For example, we look into the plane stress condition. Plane stress condition is simply plane stress condition, we understand that one of the component may be sigma 3 equal to 0 or sigma z equal to 0. So, one stress component equal to 0, but it practically applicable if when we are handling very thin sheet, load is applied on a particular thin sheet in a plane of the sheet, if load is applied, or very thin wall tube and it is subjected to some sort of internal pressure. So, in that case we can find out there is a stress components, only two stress components, that means the stress components is acting but or sigma 2 or sigma 1 is acting, but normal to the sheet, the stress is basically 0, and this is the practical aspect, because and this is a quite good assumption, the plane stress condition when you are handling very thin sheet also and with particular loading condition. So, that situation may also arise, but we will try to look into that. If this is the plane stress condition, how we can relate between the stress and strain in the matrix form, or that we will try to look into that. So, definitely that set sigma z equal to sigma 3 equal to 0, and this is the condition for the plane stress condition, that means one of the stress components becomes 0, but it is not necessary the strain will be 0 in that particular direction, there may be, we will see that. So, once set the sigma 3 or sigma z equal to 0, then epsilon 1 or epsilon x, something like that. Here in this case we just consider the previous expression that for within the elastic components of the strain along x axis. So, in this case we simply consider sigma z or sigma 3 equal to 0, and then we can get the relation between the strain and strain using this expression. Similarly, epsilon 2 or epsilon y, we can find out the relation in this case also sigma 3 equal to 0, then we can get in sigma 2 and sigma 1 in terms of that. and here you can see that epsilon 3 is also there, that means strain, but although sigma 3 equal to 0, that means stress components equal to 0 along the z axis, that normal stress components, but there may exist also normal strain component along this particular axis. So, therefore, we can see that from the expression also that epsilon 3 the strain component along z direction, here if we put the sigma 3 equal to 0, then we can get this value. It means that although sigma 3 equal to 0 strain component, but epsilon 3 is not equal to 0, some values will be there, and here you can see that sigma 1 not equal to 0, non-zero component, sigma 2 not equal to 0. Even we can see also epsilon 1 not equal to 0, epsilon 2 not equal to 0. So, that means non-zero components. So, therefore, these are the expression for particular the relation between the stress and strain in plane stress condition. So, one we say the plane stress condition. So, from the equation the stress value can be evaluated, it is simply transformation from the strain. We put the expression that strain equal to as a function of stress. Now, we have convert this variable in such a way that stress equal to in terms of the strain. To do that, some equation we can arrange in such a way that simply that sigma 1 and the first expression, it is the value of the I think sigma 2 value. So, sigma 2, put the sigma 2 value here, and then that will be represented in terms of the epsilon 2 and sigma 1. So, finally, we are getting this expression. I think even if we put the sigma in terms sigma 1 is there 1 minus nu square, and epsilon 2 also in terms of the E. So, this is the expression we can get. Now, from here we can find out epsilon 1 plus nu into epsilon 2, that is the in terms of the epsilon in terms of the sigma 1 also, but other material properties are also included here in this particular expression. Then we can find out that sigma 1 equal to, from this expression we can sigma 1 equal to in terms of this value, sigma 1 equal to E by 1 by nu square epsilon 1 and epsilon 2 and the other material parameters or maybe material properties. Similarly, we can estimate the sigma 2 equal to in terms of the epsilon 1 and epsilon 2 and relating to the other parameters. So, it is a simply conversation of the stress in terms of the strain component, and we can see that sigma 1 and sigma 2 it is associated only on the these two cases, that it is associated with the epsilon 1 and epsilon 2. This is also expression epsilon 1 and epsilon 2, these two in terms of these two variables we represent this thing sigma 1 and sigma 2. Now, we can see overall that non-zero stresses in this in plane stress condition, what are the non-zero stress components. So, sigma x or sigma 1, sigma y or sigma 2 and tau xy, these are the, or tau 1 2, these are the non-zero stress components exist in case of the plane stress condition. Now, non-zero strain epsilon x or epsilon 1, epsilon y or epsilon 2, epsilon z or epsilon 3 and gamma xy or gamma 1 2, these are the typical non-zero strain components in case of the plane stress conditions. Now, we will try to look in the other form also, because in finite element it is necessary to represent the relation between stress and strain in the form of a matrix formation or using the column vector in the vector form. Column vector form we can write out all this expression, that is the objective to look into all this expression equation in the form of a matrix equation. Now, in general we can say that stress equal to d into epsilon. So, stress equal to d into epsilon, this is the general expression between the stress and strain, but if we look into that in actual practical cases, the stress and stress components can be more also, depending upon whether it is plane stress condition, whether it is 3-dimensional stress state or whether it is plane stress condition, the values of the sigma in the column vector can be different. So, that we will try to look into that, but here d is the matrix that can be related. D actually represents, or we can say that as a function of the all the material properties. So, D can be in the form of the Young's modulus, this Poisson's ratio as well as the shear modulus. So, D in that form. So, basically it is equivalent to the sigma equal to E into epsilon. If it is one dimensional stress state, one dimensional stress is there, or uniaxial tensile testing if we consider, in that case stress is related to the strain for single value of the stress, and then simply E is the Young's modulus. But When it is 3-dimensional state of the stress or different plane stress or plane strain condition, then it will be replaced by the D, because D account the different material properties in the matrix form, that we will see. Now, here if you look into that, in case of plane stress condition, we have already seen the components of the different stress. So, then it can be represented in this particular matrix form, F sigma x equal to this E by 1 by nu square and this particular position of this matrix, this, and this is the strain component. So, here you can say this is equivalent to sigma equal to, this is equal to the D matrix, this is the strain, and in terms of the, this is the column vector, in terms of column vector it is the in the 3 by 3 matrix form. So, that is why this relates between the stress and strain in the single value. Now, we have not included the epsilon z, because that is not necessary here, because epsilon z in this case that we can keep it separate, but it is a non-zero component, epsilon z or epsilon 3, that means strain, that can be represented once we solve this equation epsilon x and epsilon y and put this value, and then you can be able to find out what is the value of the epsilon z. Now, the D matrix for the plane stress condition, it is very important, the D matrix for the plane stress condition we can say in this way also, that E by 1 by nu square 1 nu 0 nu 1 0 this thing, but you will be getting this expression if we write the linear set of the equation, 3 equations, then from this 3 equation we can convert it in the this matrix form. But here it is very important to know what is the D matrix. So, D is basically representation of the included all the terms in this D matrix is the material properties. So, in this particular form, so this D matrix is basically true in case of the plane stress condition, but in other condition the formation of this D matrix can be different also, that means elements, position of the elements can be different in D matrix in other condition also, that we will see. Now, we will try to look into the plane strain condition. Plane strain condition, when plane stress condition may be one of the strain components equal to 0, but in this case if we assume the epsilon 3 equal to 0 or epsilon z equal to 0, that indicates it is the plane strain condition. But practically this is typically occurs, the one dimension is much greater than the other 2 dimension. For example, long rod or cylinder with restrained end. So, for long rod or cylinder with a restrained end, this indicates there is a restricted deformation in the third direction. So, in that case this plane stress condition, we can put the situation, we can consider this as a situation of the plane strain condition, accordingly we can use this formula for the plane strain condition. But we will see in plane strain condition what we can relate between the stress and strain in the form of a matrix. Now, epsilon 3 equal to 0, then once we put the epsilon 3, we have already seen the epsilon 3 terms of the epsilon sigma 3, sigma 1, sigma 2. So, if it is 0, from here we can find out the relation between the sigma 3 equal to in terms of the sigma 1 and sigma 2, and only relate with the Poisson's ratio. This is the expression for the sigma 3 in case of the plane stress strain condition. Now, it indicates that although the same thing that epsilon 3 equal to 0, but sigma z it is not necessary or 3 not necessary, it becomes non-zero component. In this particular cases, in what we have observed in case of the plane stress condition also, that epsilon 3 becomes non-zero, but sigma 3 equal to was 0. So, that was the difference in these 2 cases. Now, this shows that stress existing along the definitely the z axis, even though the strain equal to 0 in this particular direction. So, then from here we can find out what is the value of epsilon 1 and epsilon 2, what is the status of this epsilon 1. In this case epsilon 1 equal to, we can just manipulate this expression, because in this case all this expression we can put the epsilon 3 equal to 0, and we can get the sigma 3 equal to sigma 3 equal to in terms of sigma 1 and sigma 2. Then expression of epsilon y, here we replace the sigma 3 value in terms of the nu into sigma 1 plus sigma 2. So, all this expression here also with the same relation, such that epsilon 1 and epsilon 2 can be represented only in the form of a sigma 1 and sigma 2. Similarly, epsilon 2 can be represented in the form of a sigma 1 and sigma 2, such that expression can be manipulated in this particular way. Now, we can see the plane strain condition, the non-zero stress component. So, sigma x is the non-zero strain component, sigma y, sigma z and tau xy, these are the all non-zero stresses, but non-zero strain components epsilon x, epsilon y and gamma xy. That means In this case there is a 2 non-zero strain components and 1 non-zero shear strain components, and other cases the non-zero stresses also, the 3 non-zero stress components as well as the 1 shear stress components becomes non-zero in case of the plane strain situation. Now similarly, isotropic linear elastic stress strain law, from the elastic stress strain curve we can estimate sigma equal to d into epsilon E. So same way we can relate between the C, but our objective to what can be the D matrix in case of the plane strain condition, that we have already seen that we have already used this expression also in the previous slide. So use this expression and this expression, from here we can represent this the stress components in terms of the strain. That means we can represent the what is the from this expression the sigma 1 in terms of the epsilon 1 epsilon 2, similarly sigma 2 in terms of the epsilon 1 and epsilon 2. So then if we convert this thing sigma 1 and sigma 2, and from there we can form the relation between the stress and strain component. This is the 3 strain component, this is the 3 stress component, and of course we have not included the sigma z in this particular expression. Sigma z with that once we estimate from here the sigma x and sigma y, then we put the value of sigma x and sigma y, then we will be able to find out what is the value of sigma z. So these are 3 stress components, sigma x, sigma y, and C is a column vector, and this is the epsilon x, epsilon y, and gamma xy. This is the this is also column vector in terms of the strain. So these are the strain component, these are the stress components, and that relation between the by the D matrix. So in this particular plane strain condition, so D matrix can be formed in this particular form. So D equal to E into E by 1 minus 1 plus nu to 1 minus 2 mu, and this is the position of the different elements of this particular matrix. So this is the D matrix for plane strain condition. Now we can see that D matrix for the plane strain condition and D matrix for the plane stress condition. In these cases the formation of the elemental position can be different, or different element the expression are different in these two cases. So even it will be different if we consider the 3 dimensional state of the stress having all the 6 components of the strain and 6 components of the stress, then formation of the D matrix or particular form of the D matrix will be different also. So it depends on the situation. So now this D matrix is very important to understand, because it will further when you do the finite element based calculation, then we have to look into that all these D matrix at the different situation. Now once we look into this finite element formulation of the in case of the stress analysis, and assuming that we will try to look into the elastic stress analysis. Now once we look into the elastic stress analysis, then it is necessary to understand the minimization of the potential energy to explain the equilibrium condition of a particular system. We can consider that if we apply some kind of the external load on a particular element, so there will be internal stress will be generated, and that so that we have considered this thing, and then with the application of the several constant boundary kinematic boundary conditions in such a way that the system will be in equilibrium, we consider in that to satisfy the equilibrium of this particular system, static equilibrium I am talking about this particular system, then it should follow the minimum potential energy of this particular system. So that is why minimization of the potential energy, if we follow the formulation for the how we can do the minimization of the potential energy of a particular system, effectively it indicates the system is in equilibrium. Then we can relate between the stress and strain, and maybe we can estimate what is the displacement field, stress field, and strain field. It is a particular finite element based problem. Let us look into the principle of minimum potential energy, something like that. Of all possible displacement configuration, a body can assume which satisfy the compatibility and the constant, whatever constant is put, or kinematic boundary conditions, the configurations satisfying the equilibrium makes the potential energy assume a minimum value. So therefore the system assuming the potential energy assuming the minimum value, and effectively indicates the equilibrium condition of this particular system. That but the system may be subjected to internal stress generation will be there, but the system will be subjected to some kind of the external load, or some constant may be there, or some kinematic boundary condition can also be incorporated in this particular system. So therefore we will see what way we can estimate the potential energy of a system, and that such that it will be the equivalent to the solving for the equilibrium displacement and stresses condition of this particular system. So therefore it is understand the minimization of the potential energy of a system to establish the formation of the equilibrium, that means for equilibrium condition, equilibrium displacement and stresses exist within this particular body. Now, total potential energy of an elastic body, definitely we are assuming this elastic body in this particular formulation. So, potential energy of an elastic body can be defined in this thing. There is the two components, one is the strain energy of this system of this particular body, and associated, and WB is the potential of the applied load. So, strain energy generation within this particular system, and one component is there, other component is the energy potential for the applied load. Considering these two components, then we will see that assuming that the force remain constant during the variation of the displacement. So, small displacement variation is there. So, in that cases the variation of the work done by the body or by the application of the loads, then EW, that means EW is the work done by the application of the load EW, such that delta EW is the potential of the and the potential of the applied load can be related. So, delta EW, what is the work done with the small displacement for the application of the external load, that is equal to the potential of the applied load delta WP, and then this is the relation between these two. Potential of the applied load is equivalent to the work done by this external load, and the relation between these two can be this delta EW equal to minus of delta WP. So, therefore, the previous equation can be written like that, delta, this is the strain energy of the system, and delta WP is the potential, the energy associated with the equivalent to the potential energy applied to the system is equal to minus delta EW. So, therefore, delta AC is the strain energy, and this comes the work done equivalent to energy associated with the work done by the application of the external for the small displacement, and this is the delta is the increment of the energy of a particular system. So, therefore, this principle follows the concept of the minimization of the potential energy of the system. Definitely this should be equal to 0, minimization of the potential energy of the system. So, therefore, the first we have to look into the expression for the potential energy of the system, such that potential of the system E equal to this is the potential energy, that means strain, it is associated with the strain energy, and this is the associated with the energy, but because of the application of the external load. So, therefore, that should be summation over the all elements, because E indicates the element number, a particular element, and the E equal to 1 to n. 1 to n means suppose in this particular domain, when you discretize in there are n number of elements in this particular domain, and we are assuming the summation of this total, this potential energy as well as the external work done, potential of the applied load, which is can be equivalent to the application of the external load in this particular case. ES is the strain energy of the element and a particular element, and EW represents the energy equivalent to the work done by the external forces. So, E is the work done by the external forces, and it represents the potential strain energy of the system. And remember, all these cases we are assuming the everything is within the elastic zone, deformation everything is the following the elastic, so it is not go beyond the elastic domain. So, therefore, part of the system such as this EW represents the energy equivalent to the work done by the external forces, that means external forces, because in the particular situation that it may be subjected to some sort of the concentrated load. In general, I am talking about, and it may be subjected to the distributed load also, and may be subjected to the body forces also. Body forces means the force distributed over the whole domain or whole body of this particular material. So, this kind of external may also act, and then basically what is the energy equivalent to by this external load in these cases also, and the same time other you are calculating what the elastic deformation, and from that what is the elastic strain energy associated with this thing, such that system becomes equilibrium if we minimize the amount of the potential energy of this particular system. But here I am looking into that we can estimate the potential energy of this particular system. So, there are two components are there in potential energy of this particular system. We will see how we can minimize this thing. Now, what is the potential energy of this particular system? We know the strain energy. First, we have to calculate what is the strain energy of this body per unit volume is given by half of the elastic strain into stress, strain into stress. So, it is something like that. Suppose one dimensional state of the stress is the this is the strain component, is the stress component, and if you look into that, so this is the within the elastic domain, it is the relation between the stress, and stress is proportional to the strain. So, it is a linear relation between the stress and strain within the elastic domain. So, that means so this indicates that this is the energy per unit volume. From the stress strain diagram we can estimate the energy per unit volume is the basically represent this area. So, area means we can see this area of a triangle half of stress into strain. So, that is when this is the corresponding strain stress value and this is the corresponding strain value. So, from there this half of this indicates what is the area of this, and that area represent what is the strain energy per unit volume. Because if you see the units of a stress, we can check also unit of a stress, say for example Newton per meter square, and strain unitless. So, Newton per meter square, either we can say the Newton meter per Newton into multiply by meter also. So, it indicates the Newton meter by meter cube, or other way joule per meter cube. So, it indicates the what is the energy per unit volume. So, basically the half of the elastic strain in the strain, that indicates the what is the strain energy associated with this particular body per unit volume. So, therefore we take the integral over the volume, and thus we can, for a triangular component, that we started with this thing, that we can consider that particular element also triangular element. So, in that particular element, one element, we can estimate what is the strain energy. It is simply integration over the volume. So, some half of stress into strain into the dV is the volume, elemental volume, we integrate over the total volume of the domain, then we can estimate what is the amount of the total strain energy associated with this particular system. But in this case we are considering the first, we are estimating what is the strain energy for particular one element. So, element can be triangular shape or element can be other shape also, but this is the general formula of this stress into strain. But if you see, there are 1, 2, 3 in a 2-dimensional state, we can say that in a 2-dimensional state we are talking about the 2-dimensional analysis. So, if you look into the 2-dimensional analysis, which is different from the plane strain and plane stress condition. 2-dimensional analysis, we are assuming the only the epsilon x, epsilon y and the this shear stress component. That means, in the 2D analysis, we have, if you look 2D analysis, the this is the stress components, these are the strain component. So, do not confuse with the 2-dimensional analysis with the plane stress and plane strain condition. Plane stress and plane strain condition, that are the two different situation in particular practical problem, which cases we can consider this is the plane strain condition. Accordingly, we can from the D matrix formulation we can do, or even it is plane strain condition. But if it is 2-dimensional stress state, then we can say these are the different stress components and this is the 3 different strain components. Now, 2-dimensional stress state, then it is a strain into stress value, strain into stress value, strain into stress. But first 2 cases is the elastic stress and normal stress and normal strain. Second case also normal strain and normal strain in other direction, and third one is the shear stress and shear strain. So, this indicates total multiplication. In general, we can say that total stress into strain, and half is also there, and integration over the volume, dV is the elemental volume, that indicates total that total potential energy of this particular element in a finite element domain. Now, with this particular element, in this case we can see that strain and stress can be represented in this way also, that in the matrix form, such that epsilon for this element is something like that, epsilon x, epsilon y and gamma xy. This is the strain component, and stress the sigma x, sigma y and tau xy. These are the stress component. In the column vector, in the form of a column, we can write these things. So, finally, we can write this compatibility, accordingly we can put the transpose of these things such that this positioning of these things can be multiplied and elements can be. So, from here to here we can see the one single strain component. In the column vector form we have written the strain component, and there is also strain component. So, epsilon E means indicates the for a particular element. So, then strain into half into dV over the integration over the volume, that indicates the total strain energy of this particular element. Now, relation between the vectors of the stress and strain is given also in this way also. The stress can be not only this thing, stress can be that D matrix, in this case in general D matrix, and then this is the total strain components. So, this is the one of the strain component and plus sigma 0. Sigma 0 is the if in the particular problem there existence of some kind of the initial stress value. So, then total stress of a particular step, this is the initial stress value plus this we can relate between the stress and strain, and that can be the other component. So, then total stress can be sigma. So, epsilon 0 can and sigma 0 are the initial strain and initial stress respectively, but in this case the epsilon the total strain minus epsilon 0 if there exists some kind of the initial strain value. So, then effective stress equal to epsilon minus epsilon 0, that can be this thing, while D is the given below. So, D matrix D can be given the different form also if we consider only the 2-dimensional stress state if we are analyzing a 2-dimensional analysis, or if you consider the plane stress condition, or if you consider the plane strain condition. Accordingly, this we can formulate the sigma can be written in the form of a D matrix, sigma equal to D into epsilon. So, sigma equal to D into epsilon. So, in general this is the D matrix. Now, once we look into all these things D matrix, now this energy can be represented like that. This is the strain component D, and this is also strain component, because this corresponds to the stress value, and this corresponds to the strain value, and this corresponds to the stress value. So, stress simply D matrix we used to relate between the stress and strain, only that purposes we are using the D matrix, and depending upon the situation different forms of the D matrix is possible. Now, this is the strain component and this is the stress component into dV, and half we just get it outside. Now, where the integral is taken over the volume of the element, particular element, and the initial stress in this case can be assumed as the 0, that means in this case is sigma 0 equal to 0. So, there is no to simplify the calculation we are assuming there is no sigma 0. So, then initial stress becomes 0 in this particular case, but there may be some initial strain also. Now, for a 2D object of uniform thickness delta V, so this is the expression, and now if you consider 2-dimensional object, so dV can be represented like that, maybe you can use the constant thickness, uniform thickness, dV can be replaced T into dA. So, T into dA, T is the uniform thickness and it is uniform, but dA can be the elemental area in this 2-dimensional analysis, and the integral is taken over the elemental area A. T here is the thickness of the body. So, therefore, this equation can be represented like that, can be written something in general form like that. We have kept dV also in this case. So, 1, 2, 3 and 4 components are there. So, therefore, 1, 2, 3, 4 components will be getting if you multiply this thing, when this simply this in the matrix form, the compatibility of the matrix can be maintained, that particular position we can keep as the transpose, where the position of the stress or position of the strain in this particular cases. So, therefore, accordingly we can put this transpose matrix T. So, have to be very careful that looking into the expression, and we can put some that whenever required to make the compatibility these things, we can put the transpose also. So, therefore, it will be getting the 1, 2, 3, 4 components in this particular strain energy component for a particular element. Now, given that this value and this value is equal, this can be equal, that is why the D is the symmetric matrix. If D is the symmetric matrix, so this value and this value can be equal. If they are equal, then we can get this value. The one term we can reduce these things, and potential energy can be represented epsilon D epsilon D epsilon 0 D epsilon 0. That is why we can estimate this thing in terms of the D matrix. So, therefore, we can get this expression equation number 29 also from this looking into the symmetric nature of the D matrix. Now, on substituting epsilon, so therefore, we have already seen for a particular element the strain can be represented the displacement field dE displacement field in the terms of the B matrix. B the strain B indicates the strain displacement relation. So, therefore, now we are converting this form of the matrix from strain to, but if you look the formation of this matrix, we have in general the potential energy we are trying to represent, that all the strain components are there. So, basically the stress value, stress components is replaced in terms of the strain. Now, this energy, all the term is basically associated to only on the strain components. Now, we will look into the relation between the strain and displacement. Therefore, if you look into that relation strain and displacement, then it will be possible to replace the strain component in terms of the displacement. So, the strain displacement relation we have already established the relation, the strain in terms of the B into dE, B is the strain displacement matrix. Now, put this value. So, dE is we can see that dE is the basically the value of, it is not exactly a variable. So, rather the indicates the value of the displacement field in the node point in a particular node. So, therefore, dE we just keep it outside of the integral form, and therefore, inside there is a B is there, B transpose dB into dV, and dE is also there, and similarly B transpose d and epsilon 0 is the initial value over the dV. So, here you can see in this case d just outside and other is the d is inside, but I think these are the whichever is the variable in this case is d, even d can be also constant because d relates only on the parameter properties of this particular elastic properties of the material. So, therefore, d can be outside of this integral. Now, looking into what we will see, what we can do, here also we can see this relation, here also we can see also in terms of the this matrix. So, now, once we get this expression, thus just replacing the strain value in terms of the B and D. So, finally, we can see that the term d is outside the integral as it represents a constant, assuming this constant. So, therefore, that is why I keep it dE is the outside of the integral. But when integrating over the volume of the element is constant, definitely over the particular element is constant, therefore, d is kept outside. Now, the term written within the first bracket can be identified as the square matrix. Say we have seen this is the identified square matrix, while the bracket within the second considered as a vector. So, therefore, this can be considered as a vector term representing this Ke and F0, the elemental strain energy from equation 3 can be represented like that. So, therefore, we can see overall the elemental K matrix, then we have seen that we can read the stiffness matrix also because B transpose dB represents the K matrix. So, from this equation we can see that K matrix also. So, this represents the, I think if you look into the K matrix expression of the K matrix. So, this indicates the K matrix for a particular element. From there we can see that this is the K matrix. So, K dE is there, half of dE is there, this dE is there, and this represents the K matrix B transpose dB, you see dE K dE. Therefore, similarly the next dE into this one, and here you can see that not exactly this represents the B transpose D and this strain components is there, but this initial strain components we can consider as a not actually variable. So, therefore, this can be considered as a constant. So, accordingly, but B is the variable quantity such that it is representing in terms of this thing F, this thing in terms of the column, in terms of the vector also F E epsilon 0, that indicates the initial strain value. But other part half of the initial strain value, if you see D value and this also epsilon 0, this I think all these cases these are the represent the constant values not varying within the element itself. So, therefore, this can be considered as a constant value. Now, K is the elemental stiffness matrix. So, K is represent the elemental stiffness matrix and this represents the load vector due to the initial strain value. So, due to the initial strain value it can be considered as a load vector. So, therefore, subscript E signifies that is the quantities associated with a particular element. So, therefore, the E indicates the Fe, E indicates the one particular element. So, basically you are considering the what is happening is a one particular element. So, for that element we are calculating all these cases. So, therefore, strain energy can be represented in this matrix form, the stiffness matrix, elemental stiffness matrix, and in terms of the load vector, that is the potential energy we represent in this way. Now, energy for external load. Now, what we can represent the external load, because we have already estimated the one value, what is the strain energy associated, but what is the associated with the external load. So, therefore, for example, distributed load along the acting edge P, then load per unit area, for example, we are assume this thing, and body force equal to W, that means per unit volume. Body force is act, but distributed load is acting per unit area, and concentrated load is exactly acting exactly one particular node. Therefore, W is the body force per unit volume. So, therefore, work done by the external load can be estimated like that. See, D displacement field transpose P into area, elemental area dA. P is the distributed load. So, distributed load, that means the integration over the elemental area is basically actually indicates what is the load, and over the area, if you see the integrand over the area associated with the distributed load, but if there is a body force, that means body force means it is acting per unit volume in that sense. So, therefore, body force into over the volume, if you put the integrand, then D is the displacement field, D is the displacement field. So, therefore, displacement field into this load or displacement into load, that indicates the work done in this particular case. So, therefore, integration done, because it is elemental area, we consider the integrand, elemental volume we consider. So, therefore, we can put the integrand sign over the volume or integrand over the area. Now, where D is the small elemental area along the edge, because the distributed load is basically the load acting, not the whole, is only on the along the edge. If it two dimensional case, it must be acting along the edge. So, over the surface area, basically the distributed load, but the dV is the small elemental volume, because body force is acting throughout the volume. So, therefore, accordingly you have to consider, and we know the D, the displacement field displacement relate to the elemental value of the displacement in terms of the shape function N, that matrix. So, therefore, we convert this in total work done in terms of the D in terms of the elemental, and N this value elemental value shape function, and in terms of the displacement value of the element particular point, and then over the area integration over the volume of this particular element, and over the surface area which is involved, basically which area is basically involved for acting the surface distributed load over the surface. So, therefore, area, and this it is acting for a particular element, the summation over the all number of elements. So, therefore, suppose there is a m number of element is basically m number of element is associated with the application of the some kind of the boundary load, that means this distributed load over the boundary, but not necessarily all the element will be acting on the subjected to some sort of the distributed load. So, therefore, this, but all element has to be considered in, if there is a this is the volumetric load, that means body force. So, therefore, E is the n number of elements, but this thing, or here m is the number of elements located at the boundary on which distributed load is acting, but small n is the number of elements for the whole domain of the analysis. So, accordingly we can find out the what is the work done because of the distributed load as well as the kind of body force. Now, total work done, we can see that it can be expressed the same, we have already shown this thing, and P and W. So, work done can be represented in terms of the, because D is the constant term, and this integrand shape function P dA, it can be represented the F E P, and this is also the, this can be represented by F W. So, it can be load vector, but load vector on the surface and the load vector over the volume. So, that means body force, basically this way we can represent these things, the total work done, and F P E, and this is kind of F W E load vector. So, therefore, additional the work done may be possible by application of the some kind of the concentrated load only acting on the various particular nodes. So, when there is a concentrated load, then total work done by the concentrated load can be done like that. So, delta displacement, a nodal displacement vector, delta for example in general nodal displacement vector, and T is the nodal load vector. So basically displacement d1 t1 basically on the one particular node, exactly on the node point the value is defined. So d1 the displacement on the particular node with the and the concentrated load is acting in this particular node. So d1 t1, similarly d2 t2, d3 t3. So basically t1 t2 t3 we represent the concentrated load which is acting exactly on the node of the different node, and definitely this node point will be concentrated load is basically acting only on the surface. So definitely it will be defined on the surface, and but particular point basically I can say the particular node point the concentrated load is acting, and d1 d2 d3 can be the overall displacement. So therefore total work done because of the distributed load acting on the surface, concentrated load acting on the node point, and body force is acting in general in any kind of particular system, then total external work done can be represented in terms of the displacement field. This is the distributed load, and this accounts the body force, and this accounts the concentrated load. So therefore when it is accounting exactly on the concentrated load in a particular node point, so we are counting the work done simply the what is the load into the what is the displacement field on that particular node point. So that is why directly delta into T we can produce there also, and here but it is integration over the, it is also required that thus load vector can be produced, but the formulation can be different as compared to the concentrated load. Now we can see the difference, this formulation or expression of the external work done if there is a concentrated load, if there is a distributed load, or if there is some volumetric load is acting in this particular problem. So then accordingly we can look into the different expression for that. Now potential energy of the system, accounting this thing, all these cases that we can see the potential energy of this system is total system can be represented like that. This is the strain energy, this cases, and this is also accounting the strain energy this case, but it is having the initial strain as considered as a load vector, and then here the concentrated load, this accounts the this distributed load, this accounts the volumetric load, external load, and this indicates the concentrated load, and this terminology in that other these are the constant terms also, but it is associated with this thing strain energy, if fixed strain energy associated with the some initial strain value accounting this one. So once we do this thing, so total potential energy of the system, this thing. Now to minimize the potential energy of the system, so this can be differentiated with respect to the displacement, nodal displacement value, then we can reach some formulation. So therefore we can see that the minimization of the total potential energy of the system E should be differentiated with respect to each nodal displacement. So delta E by d. So it should be 0. What we can solve any kind of the minimization problem also with that we find out the derivative with respect to that variable, and then we make it equal to 0, and then we find out some condition what is the to minimization of this particular system. So then once we do that, we do this thing with respect to del dE, d is the displacement of the nodal displacement field. So therefore it is a nodal displacement field we can see. So it is a basically if we look into in general some k d square is value. So once we do the half of k d square, so d by dd of half k d square we getting something like that, half of twice k into d. So basically we are getting the k into d, that will be getting. So then with respect to dE displacement, here we can getting the this term derivative k into d, and this will be always only the constant term will be there because we do the first derivative these things, and this there is some displacement field also there, it is associated with the dE. So this term will directly come and this term will directly come. So this 3 term, because this was the accounting the displacement field. So therefore we do the first derivative, but this is the concentrated load, delta is the nodal displacement field also, then only the T will be coming this picture, but this is the constant initial strain. So therefore if you do the derivative we have count this derivative equal to 0. So then if you do thus minimization total potential energy, do the derivative this thing, this is the general expression in the matrix form also you can get by following the minimization of the potential energy, make it equal to 0. So therefore contribution from the all element we can finally reach that k delta, this is the contribution from the all element, means we are basically estimating for one particular element, making the summation of the contribution from the all element, and in general way we can find out once the contribution from the all element, and this is the stiffness matrix K, and delta is the displacement field. At delta we have already defined this delta equal to nodal displacement vector. So, overall nodal displacement vector for the considering for the all nodes point. Then F load vector, it is also load vector, it is load vector, concentrated load, distributed load vector, this is the volumetric load vector, and this is load vector because of the initial strain value, make it equal to 0, and then this is the general formulation after contributing from the all elements contribution, and K is, it is called the stiffness matrix. Now, we can see this is the general formula for the minimization of potential energy, and we can see the K equal to the stiffness matrix. K is the B transpose dB, dV over the volume, and contribution from the all element. F initial for the initial strain component, and here you can see contributing from the all element B transpose D, but this will be the initial strain value. Then distributed load can be defined, but distributed load can be this can be different from N also, but we are in general we are counting the all element, but not all element may involve for the distributed load. So, maybe selective load can be may be applied for as a boundary interaction for a distributed load. So, then accordingly you have to decide the N value. It is N transpose P per unit area, it is P should be defined the application per unit area, and similarly this can be defined for the whole domain for all element because it is a volumetric load. So, then in this case W can be defined the per unit volume. So, these are the expression matrix forms. Then once you do the integration one particular element and the sum of these elements, this will be able to get the value of the K, but of course once we do for the one element do the calculation, then we form the K matrix for the assembling from the contribution from the all elements. Then finally, we can pull the full stiffness matrix. Now, T indicates the external concentrated load, this can be directly be applied at the particular node value. So, finally, we can reach the in general expression K into delta equal to F. So, it is a vector form, we can say the column vector, K is the stiffness matrix, D is the displacement field. So, therefore, here we can solve for delta from this equation. So, that is the in general form of the stress analysis or elastic stress analysis, we can form the K into delta minus F equal to 0. So, we can go for the solution for the delta, because delta indicates what is the displacement for the each and every node point. So, once we get the solution for the delta also, then from the delta we can find out what is the strain value for the whole domain. So, then by looking into the relationship between the strain and displacement, once we get the strain value, then we can find out what is the value of the stress, because by looking into the relationship between the stress and strain value, we can find out the stress value. So, this is the in general procedure for solving the stress analysis problem, but following the minimum potential energy. Now, we will try to apply this form this expression to look into the other how we can solve, what we can progress for the elastoplastic analysis in case of the general stress analysis model. So, thank you very much for your kind attention.